Okay, let's go through the discussion too. First, the problem one. We have the u1 to un, they are random variables. And un has a distribution exponential n. That means that un has the density like this, n e to the power negative n u. And indicate the function u greater than 0. Okay. And we want to claim the un is converged to 0 in probability. So here we have to use the definition 1. Okay. In definition 1, if we want to say Sn converges to x in probability, that means we have to check for every epsilon. And if the difference of Sn and x greater than epsilon, and we have to show the probability of this event go to 0 as n go to infinity. Okay, so in problem 1, we have to show that the probability of the un minus 0 greater than epsilon. For every epsilon larger than 0, this one will go to 0 as n go to infinity. So this is question mark. Okay. And here we know this one is equal to probability of un absolute value greater than epsilon. And this is equal to probability of un greater than epsilon. This is because the exponential distribution is positive. And this can be looked right into the integration from epsilon to infinity, and the density of un, which is n e to the negative n to u du. Okay, and we know how to integrate the exponential function. So this is equal to negative e to the negative nu from epsilon to infinity, and the answer will be e to the negative n epsilon. And this go to 0 as n go to infinity. So we can say un converges to 0 in probability. Okay. And the question 2, we have u1 to un, they are independent, uniform distribution, and we define Sn, which is the maximum value of u1 to un, and want to prove this value converges in distribution to exponential 1. Okay, so in here we have to use the definition 2. In definition 2, we say if Sn converges to x in distribution, that means we have to check the PDF or the PNF or CDF converges to Sn of Xn converges to the PDF or PNF or CNF of x. Okay, and in this question, I want to do the thing like this. For every t below to the real number, and probability of n 1 minus the Sn, the maximum value, greater than t, converges to the probability of x greater than t. Here x is the exponential function with the parameter 1. So this means the probability should be e to a negative t. Okay, and we have to show this. So this is a question mark. So here is the CDF of n 1 minus Sn. And this one is the CDF x. So from here, we can if we can this, that means we have shown the CDF of this value converges to a CDF of x. So that means this number converges to x in distribution. Okay, so we have to prove this. Okay, the probability of n 1 minus Sn greater than t. Okay. This is equal to the probability of 1 minus Sn greater than t divided by n. And we do some rearrangement, then we can see it should be like this, greater than Sn. Okay. And from the definition, we know that the Sn is the baseline value of u1 to un. So this is like this. Un. Okay. Also, here we know that this is 1 minus Tn greater than ui for all I from 1 to n. Because this number greater than maximum value, that means all the number ui are smaller than this number. Okay. And next step we use the independent of u1 to un, and we can show that this is equal to product of 1 to n. Okay. And then we use the identity of u1 to u, because we know u1 to u are all come from the same distribution, so we can write as this with power n. Okay. And then we know that u is the uniform little 1. So that means this probability is 1 minus t divided by n with power t. And from the calculus, you know this value will convert to e to a negative power t. Yeah. So this value is the same as the CDF of x. So we can say the n times 1 minus the maximum value converges to exponential distribution. Okay. Okay. The next question. Question 3, we have S1 to S100. Now independent Poisson distribution with parameter 1. And we want to use the normal approximation, that is central limit theory, to approximate the probability that the summation is between 90 and 110. Okay. So we want to scandalize the probability, want to find this I from 1 to 100, Si greater than 90, smaller than 110. Okay. And first we have to say we know the mean of x equal to 1 and the values of x are also equal to 1. This is because S is come from the Poisson distribution. Poisson 1. Okay. And we want to do the standardize of this quantity and then use the central limit theory. So while we have the first thing, we want to find the average of this. So we divide it by 100. Okay. Okay. As you can see, this value is the sample mean. So This is the sample mean. We want to use the, okay, and this value is 0.9 and this is 1.1. So the sample mean minus its mean, S bar minus 1, 1.1 minus 1, and 0.9 minus 1, and that divided by its values over square root of sample size. So this is negative 0.1. Okay. So it is a negative 0.1 divided, okay, 0.1, okay. So we want to divide it by the variance, which is 1, and the square root of sample size, which is 100. So you look at this. And we can calculate these two values, which is negative 1 and 1. And this is the standardized of the S bar. So this is approximated by Z by the central limit theory. So we can say the probability is approximated by negative 1 smaller than Z greater than negative 1 smaller than 1. Okay. Okay. So by the central limit theory. Central limit theory. Okay. The next day you can use the R or the Z table to find the probability. Okay. Okay, as you can see, in the central limit theory, we only need the mean and variance. So, but the question gives us the Poisson distribution. And we can use the Poisson distribution to find the mean and variance, and use the mean and variance to find the standardized of the central mean, of the sample mean, and then we can use the central limit series to approximate the standardized sample mean. And then, because we know how to calculate the probability of the standard normal distribution, then we, okay, maybe this is normal 0, 1, okay. And we usually use Z to refer a normal distribution. Yeah. Okay. Yeah. So if you can get the Z in here, then you can find the probability by R, or you can use the Z table. Okay, that's today's discussion.